Okay, good morning. Welcome to
FamilyMath568.
FamilyMath568. So, in the last few weeks, you guys have gotten pretty interested in playing different card games, right?
Yeah.
What's your favorite game?
Poker.
Yeah.
Poker? Okay. What other games have you learned how to play?
Rummy.
Rummy?
Yep.
Kings in the Corner.
Kings in the Corner. Okay, yeah, so lots of fun games. But as a result of that, you've gotten pretty interested in shuffling, right?
Yeah.
And it's actually a really interesting question, how you can tell if a deck is really well shuffled or not.
Yeah.
In fact, when I said yesterday we could figure that out, what did you tell me? Do you remember?
I didn't think it was possible.
You didn't think it was possible.
Because mixed up is kind of relative.
Yeah, so we've labeled our cards from 1 to 52 for something later in the project. But right now, this deck, we would say, is not pretty mixed up.
No.
Right.
It's just all in suit.
All in suits. Yeah, and then the suits are in order.
Yeah.
Okay, and we got a lot of 52 cards here. What do you think? Do you think there's a way we can tell if a deck is mixed up versus not mixed up?
Well, maybe, like, we have the cards based here on, like, suit, so 1 through 13, I think.
Uh-huh.
Is
Well, ace through 13.
diamonds.
Yeah.
Then, well, maybe.
You could kind of look at how far away the numbers range from each other
Okay.
with that, because if you had all these right next to each other, it would not be a very shuffled deck.
Yeah.
We could, like, look at how far this card moved from where it starts. Maybe. But then there'll be some cases where it would be considered by that way to be shuffled, but we wouldn't consider it to be shuffled.
Oh, good. Like, what's an example?
Like, all these 4 groups of 13 just shifted places.
Right. We shifted the groups of 13 around, but kept the groups together.
Yeah.
And then that wouldn't actually be very shuffled, even though the cards may have moved reasonably far from their starting position. Yeah, so this is actually a very challenging problem. And it uses a concept that you guys have not, probably at least not ever heard before, called entropy. You heard that word before?
No.
Entropy is, think of it as being a measure of how mixed up things are. And so we're going to use a specific idea called Shannon entropy. Which was introduced in the last century by a mathematician who, actually I should have done a little more research on him. I'm pretty sure he was actually at MIT, Claude Shannon. And he was a big and very important mathematician in the 1900s. Actually, in the late 1900s. And his biggest contribution that he's known for is what's called information theory. So basically how you transmit information to say things on the internet going back and forth. But he has introduced this idea of entropy, a specific kind of entropy that we're going to use today to look at card shuffling.
Okay.
And the only tricky thing about entropy is it uses a logarithm function. It uses a function. I'm going to use a function called ln just because that's on my computer. lnx. You've seen logs before, right?
Yeah.
But you haven't. This is the log base e. I'll introduce logs very quickly by introducing log base 2. All the logarithm does is measure the power. If we look at powers of 2, it measures the power that you need to get to this number. So for 2, what power do I need to get to 1?
You need the
2 to what power is 1?
to the 0.
Yeah. 2 to what power is 2?
1.
2 to what power is 4?
2.
2 to what power is 8?
3.
Yeah. And then for numbers that aren't powers of 2,
It's
the
kind of
logarithm
like in
is
the
going to
middle.
be in between.
So like 3 would be 1.5.
Well, it'll be around 1.5. Similarly, when you're between 4 and 8, like 5, the logarithm of 5 will be close to 2. Maybe it'll be 2.2. The logarithm of 7 will be close to 8. So it's just asking what power do I need to get to a specific number.
Okay.
With the natural log, instead of asking powers of 2, which I think Shannon entropy actually uses log base 2, with natural log, it's asking what power of e do I need to get there. So e is about 2.718. So the natural log of 1, what power of e do I need to get to 1?
Well, e to the 0.
E to the 0 is still 1. What about 2? What power of e do I need to get to 2?
Well, it's not going to be an integer.
No, it's not going to be an integer.
So.
Will it be bigger than 1 or less than 1?
It'll be, I think, less.
Less than 1, yeah.
Because
So it'll be less than 1. What power of e do I need to get to 4?
around.
Probably a little
2?
less. Little less.
Little less than 2.
Well, e is very nearly 3, right?
So maybe.
Like around 1.5 or so.
Okay, so a little bit bigger than 1. 8. Do you think 2.718 squared is bigger than 8 or less than 8?
Well.
What's 27 squared?
27 squared is 729.
729. So that means 2.7 squared is probably what?
7.29.
Yeah, so what do you think?
So maybe.
8. What power of e is 8?
Around. Maybe around 8. Maybe around 2.
2, yeah, and a little bit bigger than 2. So that's just the natural log of it. All right.
Okay.
Okay. Good work.